We've talked previously about the kinetic energy, and I told you at that point that the kinetic energy was simply half mv squared, and that was the whole story. And in some sense, it kind of is, but there is an addendum to that, which is when you talk about half mv squared as being the kinetic energy, you are assuming you're talking about an object whose center of mass is moving at speed v, and it's actually like an object moving from one place to another. In which case, everything is very simple and fine, and this all works out. But things get a little bit more complicated if you have an object which is spinning, but which isn't actually moving anywhere on the whole. For example, think about like a spinning top. A spinning top clearly has motion, it clearly has kinetic energy, but velocity of the center of mass of the top is 0 because it's just spinning in place if it's just a stationary top. So how do we handle calculating the kinetic energy of an object like that? So first of all, in terms of the terminology, half mv squared, sometimes people call that the translational kinetic energy, because that's the kinetic energy of something which is moving from over here to over here, translating, as they say, from over here to over here and actually moving around. There is another closely related way that you can calculate the kinetic energy of an object that's spinning, and this is referred to, not surprisingly, as the rotational kinetic energy. You can probably actually guess what the formula for the rotational kinetic energy is going to be if you think about it for a few minutes, because you already know from previous knowledge in the course that the rotational version of mass is moment of inertia, and the rotational version of speed is angular speed. So not surprisingly, the way you calculate the kinetic energy for rotation is just by replacing the inertia with the rotational inertia and replacing the speed with the rotational speed, and you end up getting kinetic energy is half I omega squared. So I is the moment of inertia, and omega is the angular speed of the rotation. So like with the translational kinetic energy, this rotational kinetic energy cannot be negative. Doesn't matter if omega is positive or negative, the kinetic energy turns out to be positive. And of course, the moment of inertia can't be negative. So the rules for how you handle rotational kinetic energy are exactly the same. So there's really nothing new to say here. The only difference is it's a little bit more complicated to calculate. And finally, I wanted to also mention that there may be some cases where you just have translational kinetic energy. For instance, if you have an object that's just moving around, there might be some cases where you have just rotational energy, like the spinning top I mentioned. It's spinning in place, but not actually going anywhere. And there are also cases where you have both translational and rotational kinetic energy. Like, for example, if you have a rolling wheel is simultaneously spinning and moving forward at the same time. So if you're dealing with something like that, which is spinning and moving, you simply calculate both types of kinetic energy and add them together. Because as with potential energy, the total energy is just the sum of all the individual types of energy. So you can calculate one of these, or you can calculate both of them and add them together as needed, depending on what's actually happening in the problem you're solving. But other than that, you just put these energies into conservation of energy equations exactly the same way as you would with other types of energy, and as with the translational kinetic energy.